All right, thank you so much for joining us today. So, as I said in the previous video, I just jumped L'Hopital rule because we wanted to talk about, how to differentiate some of the function before we can start the L'Hopital's rule. So, L'Hopital's rule is kind of like, okay, for example, we know that this function here, this function that is here, we can basically write it as like 2 out. I'm not writing the limit. Okay, let me write the limit attached to that. X is approaching 1, 2x squared minus 1 divided by x minus 1. And we can write this one as x is approaching 1, 2x minus 1, x plus 1 divided by x minus 1. And we can cancel and we can solve this one and get something like 4, right? But the question is saying that if we can plug in 1 inside this function direct and get, so when I plug in, I'm going to have 2 minus 2 divided by 1 minus 1, which is 0 divided by 0. So if I have something like 0 divided by 0, then we can think of using what? The L'Hopital's rule. So what we are going to do here is we are going to talk about some of the forms that we can see that is going to help us to use the L'Hopital's rule to solve some of the questions instead of trying to do simplifications and those kind of things. And then we just use the L'Hopital's rule and then we just go. So we are saying that we have f and g and they are differentiable on the open interval, right? And then such that when I differentiate the function, it's not equal to 0, right? But when I plug in the limit, we are assuming that they are all giving us 0. So the top is giving me 0, the down 2 is also giving me 0. This one should be x, right? So that is basically what we are doing here. So if that's the case, if when I find limit of this and I'm getting 0 and limit of this I'm getting 0, then we are saying that this is the same as just differentiating the function here and differentiating the function here. Please pay attention to this one because L'Hopital's rule does not go with the quotient rule. How did I do this from here to here? I just differentiated the top and differentiated the down. I didn't say this is a fraction, so I need to use the quotient rule. We are not using the quotient rule. Just differentiate the top and just differentiate the down. So we are saying that when I pick limit on this and I'm getting 0, and when I pick limit on this and also I'm getting 0, then we can use the L'Hopital's rule to go through the process. So let's see that. Now, let's see some of the forms. So I'm going to pick them one by one. We are going to look at some function that when we are doing direct substitution, we are going to get something like this, and we use the L'Hopital rule to solve this one too, and then we talk about this one too. Before now, I can give you another form where we need to use the non-constant base idea to solve, right? So we are going to solve all of them together, and then I'll give you a trial question to do. So I'm starting with this. So anytime I want to use L'Hopital's rule, the first thing I need to do is I need to put it direct and see what is happening. So solving this, I'm going to set x to be equal to 4 and then just put it inside direct. So 4 squared minus 7 times 4 plus 12 divided by 4 squared minus 16. And this is going to give me 16 minus, this is, I think, 24. Is it 24? 7 times 4 is 28. Plus 12 divided by 16 minus 16. And we see that this is going to give us 0 divided by 0. Is that right? So since this is 0 divided by 0, then we can apply the L'Hopital's rule, right? Even though maybe we can simplify this, but if this one holds for the L'Hopital's rule, then we can use the L'Hopital's rule to solve. So this is what I'm going to do. This is how L'Hopital's rules move. We said if I have limit as x is approaching f of x divided by g of x, and this is giving me 0 over 0, one of them, this or that, then this one will now move to limit as x approaching a, I'll differentiate f, and then I'll divide by differentiating g of x. So this is like f of x, and this is like g of x. So it means that this we are going to have limit x is approaching 4, x squared minus 7, x plus 12 divided by x squared minus 16. This will be equal to, but I'm putting something here, LH. This is trying to tell me that I'm using the L'Hopital's rule. So I'm just moving from the original limit, I'm moving to L'Hopital's rule. So I'm coming to apply the L'Hopital's rule. So now this is going to give me limit x is approaching 4. Then I differentiate the top. So that's the reason why I said let's do differentiation before we come here. So differentiate 2x, x squared get 2x minus 7 divided by 2x. Now, one thing about L'Hopital's rule is you can do the differentiation so it does not give you something like 0 in the down, right? So now that I'm done with the first differentiation, I need to do direct substitution and see if I'm going to get a result. If not, then I need to differentiate it again. So let's try and plug in x is equal to 4 and see what we are going to get. So this is going to give us 2 times 4 minus 7. 2 times 4. This is 8 minus 7 divided by 8, and this is going to give us 1 over 8. So this is going to give us 1 over 8. So if we are not using the L'Hopital's rule and you simplify this, you will see that your final result is going to be 1 over 8. So basically that is the idea of solving this. Good. Now let's look at this one. You remember this one, we said this is a property which is equal to 1, right? When x is approaching 0, sin x over x is 1. Now let's use L'Hopital's rule to solve it and see. Now the idea is that when I set x to be equal to 0, this is going to be sin 0 divided by 0. Sin 0 is 0, so I'm getting 0 over 0. So it means that we can apply the L'Hopital's rule. So always, for me to apply L'Hopital's rule, sometimes I need to show this before I start using it. But if it is section A or objectives, then you can just, if you see that it is true, you can just do it that way and then you just go. So this one, don't forget, I put my L'Hopital on it, telling me that I'm going to apply the L'Hopital's rule. So limit x is approaching 0. When I differentiate sine, I get cos x divided by, when I differentiate x, I get 1. So what I need to do is now, as soon as I'm done with the first derivative, I plug them in and see if it is going to work out. So x is going to cos 0 divided by 1. Cos 0 is 1 divided by 1, and this is 1. And indeed, we saw that this is supposed to be giving us 1. So that is how the L'Hopital's rule works. Let's take more example here too. We see now same thing for this one. Plug in s is equal to 0. You are going to have 1 minus cos of 0 divided by 0 squared. The top will be 1 minus 1 divided by 0, and you get 0 over 0. So it means that this one too, we can use the L'Hopital's rule. So let's go. Limit x is approaching 0. 1 minus cos of x divided by x squared. This is going to use the L'Hopital's rule, and this is going to give us limit x is approaching 0. When I differentiate 1, I'll get 0. And then when I differentiate cos, I'll get minus sign. So I have minus and then minus sign. So it's 0. Let me put the 0 there, minus sign. Divided by, when I differentiate x squared, I get 2x. So the question is, I need to simplify and see if I can put in the value in. So when I do that, I'm going to have sin x divided by 2x. When I set this one to 0 and I put it inside, I'm going to have sin 0 divided by 2 times 0, and this is 0 over 0. So I need to apply the L'Hopital's rule again from here, because when I did the direct substitution, it didn't work. So I need to apply the L'Hopital's rule again. So I'll move again, putting LH, meaning that I'm come to apply the L'Hopital's rule again here. So let's go. This is going to give us limit x is approaching 0. When I differentiate sine, I'm going to get cos s. Then when I differentiate 2x, I'm going to get 2. Then I do direct substitution by setting s is equal to 0, and this is going to give us cos of 0 divided by 2. Cos 0 is 1, and this one is 2. So this is going to give us 1 divided by 2. 1 divided by 2. So basically that's what we are going to get from this function. Now let's look at this one too here. Now this is kind of very nice. Plug in infinity and let's go. This is going to give us ln of infinity divided by infinity. Ln of infinity is going to give us infinity. So this is kind of infinity over infinity. So we can also apply the L'Hopital's rule again. So limit x approaching infinity, natural log of x, applying the L'Hopital's rule. So I'm going to have limit x is approaching infinity. When I differentiate a ln function, what am I going to get? 1 divided by x divided by, when I differentiate x, I'm going to get 1. So when I simplify this, I'm going to have ln x approaching infinity, 1 over x. Let's plug in infinity and see what we are going to get. So 1 divided by infinity, and 1 divided by a big number, it's a big 0. So we are going to get 0 for this one. Okay, so now you see the way we are practicing and seeing how things are going. Let's take more example, then we move to the next form. Let's plug in 0 again. E to the power 0 minus 1 divided by 0 squared plus 3 times 0. This is 1 minus 1 divided by 0 plus 0, and this is 0 divided by 0. So we can apply the L'Hopital's rule to the function. Minus 1 divided by x squared plus 3x is equal to. So this is kind of something like this. So we have different examples. We will take the next form right now. I think after this page, we should be able to do that. So when I differentiate e to the power x, what am I going to get? We know how to do differentiation, so this will be that. And when I differentiate 1, I'm going to get 0. When I differentiate x squared, I get 2x plus 3. Now, I want to simplify this, and then x, I get 0 e to the power x divided by 2x plus 3. Let's do direct substitution. Set x to equal to 0. We get e to the power 0 divided by 2 times 0 plus 3. This is 1 divided by 0 plus 3, and this is going to give us 1 divided by 3. So using L'Hopital's rule is kind of very nice, but you need to make sure that the property is satisfied. If not, when you do it, you are going to get the answer to be wrong, even though you can use the L'Hopital rule to get a question. I should have thought about it and bring a question that we cannot use the L'Hopital's rule to do it. And then you see that you do the L'Hopital's rule, it's not going to be the same as when you evaluate the limit. Now let's do this one, then we move to the next form. So plug in 0 sine 3 times 0 divided by 2 times 0. This is going to be 10 sine 0 divided by 0, 0 divided by 0. So we can use the L'Hopital's rule. So limit x is approaching 0, 10 sine 3x. So you see that this one was very good for us to, talk about differentiation before, talking about L'Hopital's rule, because basically here we are doing differentiation, and if you are not good with the differentiation, we see that you are going to have some difficulty here, right? So basically that's the reason why we started with differentiation. Now, how did I differentiate this? I maintain my 10, I differentiate sine, I get cos, then I finish, I need to differentiate what is inside, getting 3. I differentiate 2x and I have this. So this is going to give us limit x approaching 0, 30 cos of 3x divided by 2. Now I can set x to be equal to 0 to verify and see. So this is 3 cos, when I put 0 there, to be 0 divided by 2. Cos 0 is 1 divided by 2, and this is going to give us 3 over 2. It's kind of very nice. Yes, it's kind of very nice. Yeah. So that's what you are going to get at the end of the day. All right. So let's look. Oh, I think this one is 3-0. No, I didn't say this is supposed to be 30 here. So this is going to be 30. This is going to be 30, and this is supposed to be is it 15? Yeah. So this one is 3-0 here. I didn't say that 0. Yeah. So now let's look at another form, right? So the other form, the one that we looked at, was 0 over 0 and then infinity over infinity, like something like that. And let's look at when it is 0 times what, let's say infinity or infinity minus infinity. So what are we going to do? So here we are looking at the where x is approaching positive, like 0 from the positive, because len function cannot take negative value, right? So when I put this one inside, I'm going to have 0 to the power 3. So here I'm setting x to be 0. But the idea is that the plus here is telling us that we are coming from the positive side. And then len of 0. So this is going to give us 0 times. Len of 0 is infinity. What's len of 0? I think len of 0 is negative infinity. So getting something like this. I think we can add that form to it. Maybe 0 times negative infinity is just the same. So len of 0 is negative infinity. Let me just prove it for you to see. We know that e to the power minus infinity is 0, right? So e to the power a very big number, negative big number is 0. So I pick natural log on both sides. And then this will cancel this. So I'm going to have infinity, which is equal to len of 0. So this kind of something that you can have it in mind. Yeah, so maybe I can squeeze this up there so that you can have it in your mind somewhere here. Good. Now let's continue. So it means that now we can also apply the L'Hopital's rule to it, right? So let's see what we can do. Now, you see, the L'Hopital's rule should be always in terms of like something over something, right? So as we started the L'Hopital's rule, we are saying that we should have in something like this over this. So what we need to do is we are going to write this function in the form of something over something. So limit as x approaching 0, len of x. I'm going to write this one as limit x approaching 0, len x divided by 1 over x to the power 3. Do you agree? So this is the same as that, because what I've written here is like 1 divided by 1 over x cubed, and this is the same as x cubed. So this can be written as this. Like, since I have division here, so it means that it's 1 divided by this, like this, and this is going to give us something like this. So now that we have it in this form, then we can do what? We can now differentiate. But for me to differentiate, I would like to write this one in this form first. Limit x is approaching 0, len of x divided by x to the power minus 3 before I will apply the L'Hopital's rule. So let's go through the process. What are we going to do? We are going to have x approaching 0. When I differentiate len x, I'm going to have 1 over x divided by, when I differentiate x to the power 3, I have minus 3x to the power minus 4. Is that right? Yeah, that's true. So what am I going to get from this side? Oh, don't forget this is from the positive side. Good. So let's try and simplify this. And we are going to have limit x approaching 0 from the positive side. This is going to give us something like 1 divided by x times okay, so this one can be written as times 1 divided by, okay, so let me just, yeah, divided by, so 1 over x divided by, then I write this one as divided by minus 3 divided by x to the power 4. Yeah, so this one will be good. And then limit x is approaching 0 from the positive side, 1 over x times this divided by 3. Good. Then we can write this one as limit x approaching 0 from the positive. 1 of the x will cancel this. So this is going to give us minus x to the power 3 divided by 3. I plug in the 0, and then I'm going to have minus of 0, 3 divided by 3, and this is going to give us 0. So that's what we are going to get at the end of the day. It's kind of very nice. Good. So let's look at this guy too here. This is going to give us plug in infinity, e to the power infinity times 1 over infinity, and this is going to give us infinity times 0. So we can use the L'Hopital's rule to solve. This one is in the form of the the function already. So x e to the power x over x. This is using the L'Hopital's rule. We are going to have something like this. limit x approaching infinity. When I differentiate e to the power x, I get e to the power x. When I differentiate this, I'm going to get 1, and this is going to give us limit x is approaching infinity, e to the power x, and this is going to give us e to the power x. E to the power infinity was the same as infinity from question 2. Let's take some 1 or 2 examples again, and then we talk about, then we are going to talk about when we have it in different form, right? So now let's look at this. This one, we are coming from the negative side, right? So let's plug in infinity, right? But what we need to do is I can write this one as limit x is approaching pi over 2 from the negative side. From the negative side. Now we know that sec is 1 divided by cos x, right? Minus tan is sine x divided by tan x. Sorry, cos s. Good. So now we can now plug it in and see what is going to happen. So 1 divided by cos pi on 2 minus sine pi on 2 divided by cos pi on 2. So what are you going to get? This is 1 divided by 0 minus, this is also cos 90. Sine 90 is 1, so 1 over 0. And this is kind of crazy, right? So this is kind of like infinity minus infinity, right? So I'm going to get something like this. Good. So if this is infinity minus infinity, then we can now use the L'Hopital's rule, because we saw this like kind of infinity minus infinity here. So let's try and then use the L'Hopital rule to do that. So L'Hopital's rule, always we need to have it in this form. So we are going to do it this form, and then we solve it. So limit x is approaching pi on 2 minus 1 over cos x minus sine x divided by cos s. This is using the L'Hopital's rule. We are going to have limit x is approaching pi minus, when I differentiate 1, I get 0. When I differentiate cos, I get minus sine. Then minus, when I differentiate sine, I get cos. And when I differentiate cos, I get minus sine. So when you simplify, this is going to give us limit x is approaching pi on 2. This will be 0 minus cos 0, cos x divided by, so this one will be plus because there is minus here, sine x. So let's try and simplify this and see if we are going to get it right. So 0, the 0 will just go. So we are going to have cos pi on 2 divided by sine pi on 2. Cos 90 is 0, sine 90 is 1, and this is going to give us 0. So indeed, we are getting 0. So that is that for question 3. Yeah, so let's look at different form, right? Now, different form, this one will be the last one, then I'll give you the trial question to do. And then different form, this one is kind of very, we are going to use a constant base idea to solve this. It's kind of very interesting and tricky too as well. So in this form, we are going to apply the natural logarithm and then L'Hopital's rule too at the same time, right? So let's take some example and see. So you see that this is kind of the non-constant base function, right? So if you are differentiating this, you need to take the natural log. That's why this one is also going with the natural log. So what am I going to do? Anytime I have some function like this, I try to plug in 0. So this will going to be 0, 0 squared, and this is like 0, 0. So it's one of this. So we can use the L'Hopital's rule to solve. Now, anytime you start function like this, you are going to assume that you know the final answer to this, right? So we are going to assume that we know the final answer to this. And this is what you are going to do. If we assume that we know the final answer to this, let's assume that the final answer to this is L. So we are assuming that we know the answer, right? Then if that's the case, then since now we are saying that this one is equal to L, then it will help us to pick the natural log, right? So this one is like we differentiating something, y is equal to x to the power x squared. Remember when you're talking about non-constant base. So we need to pick the natural log on both sides, and then we just go through the process. So that's what we just want to do. So let's see what we can do. So now take the natural log, and we are going to have limit x approaching 0 from the positive. I pick the natural log of this guy, and then I pick the natural log on this guy because I need to take natural log on both sides. And then when I do that, this guy is going to drop down. So I'm going to have limit x is approaching 0 from the positive, x squared natural log of x is equal to So I'm going to have something like this. Then when I'm done, what I'm going to do is, now you see that now we have gotten this in the form of the L'Hopital rule, right? But the L'Hopital's rule, for us to apply the L'Hopital's rule, we need to have a function f divided by a function g of x. So because this is a product rule, I need to write it in different form. So this one can be written as limit x is approaching 0. Now I can write this one as natural log of x divided by 1 over x squared. So anytime you have something like x squared multiplying this, you write it as 1 over x squared, something like this. And this should be the same as ln of L. Good. Now let me continue from here. Now let's apply the L'Hopital's rule on this side, right? So we are applying the L'Hopital's rule from this side. So let's write this one last simplification so that it can help me to differentiate that. Natural log of x, 1 over x squared is the same as minus x to the power minus 2, which is equal to ln of that. So let's do this. I want to apply the L'Hopital's rule here. So I'm going to have limit x is approaching 0 from the positive. When I differentiate 1 over x, when I differentiate this, I'm going to have negative 2x minus 3, and it's equal to ln x. We are not differentiating this because the L'Hopital rule is applying to only the limit function. So simplify this, and you are going to have limit x is approaching 0 from the positive side. This is 1 over x divided by, this one can be written as minus 2 divided by x to the power 3. Good. So limit x is approaching 0 from the positive. This is 1 over x times x cubed divided by minus 2, which is also the same as this again. And then limit x is approaching 0 from the positive. One of the x will cancel, so I'm going to have x squared divided by minus 2 is equal to the natural log of L. And then now we can plug in 0 and see what happens. So 0 squared divided by minus 2 is equal to natural log of L. And this one is going to be 0 is equal to natural log of L. Now we are assuming that the answer is what? L. But what we've gotten here is the natural log of L, not L. So what we need to do is we need to make sure that the L stand alone. And if we want to do that, since we have the natural log, we need to apply the exponential function on both sides. So I have e to the power 0 is equal to e to the power natural log of L. And e to the power 0 is 1, and this one is also L. So you see that this limit here, when you use the L'Hopital's rule to solve, this is equal to 1. So my L is equal to 1. So since my L is equal to 1, it means that this limit is equal to 1. So you see, when it's in this form, it's kind of, you need to do a lot of work. You need to use the idea of constant base, like the way you apply natural log on it, and then now you come and apply the L'Hopital's rule when you get to this side, and then you go through the process. Let's take another one. Then I think we'll take 2 or 3 more examples, and then I'll give you your trial question. So the same idea here. As we said, when I plug in 0, 1 plus 4 times 0, all to the power 3 over 0, and this is going to give us 1. 3 over 0 is infinity, so this is going to give us 1 to the power infinity, which is one of them. So 1 to the power infinity, one of them. So we can use the L'Hopital's approach to solve. So always we assume that we know the limit. So let me assume that the limit is equal to this. So this is going to give us something like this. So I'm assuming that I know the limit for this. So 1 plus 4x to the power 3 over x is equal to L. So you go through the same process again. Pick ln on both sides. So limit x approaching 0, limit ln of 1 plus 4x 3x is equal to ln of L, and then limit x approaching 0, 3 on x will come down, then multiply by 1 plus 4x is equal to ln. So this is already in the form of what, like a function divided by a function. So this is like 3 ln x divided by x. Let me write it word for you to see. So this is the same as 3 1 plus 4x divided by x is equal to ln x. So here we can apply the L'Hopital's rule to solve. So let's do that. So we can just do this. So now let's apply the L'Hopital's rule. So limit x approaching 0, differentiate this. What are you going to get? How do you differentiate a ln function? 1 divided by what is inside the bracket, 1 plus 4x, 1 divided by what is inside the bracket, 1 plus 4x, times you differentiate what is inside the bracket, also going to give us 4, divided by, when I differentiate x, I get 1, times it's equal to the natural log of L, right? So I just differentiated this. I'm having this here. Then limit x is approaching 0, 3 times, this is going to give us 4 divided by 1 plus 4x is equal to ln 1, because this is divided by 1, so just go away. So can we plug in 0? Yes, we can do that. So let's try and simplify. When I plug in 0, I'm going to have, or let me simplify first. X approaching 0, this is 12 divided by 1 plus 4x is equal to ln of 0. And when I plug in 0 here, I'm going to have 12 divided by 1 plus 4 times 0 ln L. And this is going to give us 12 is equal to ln L. Then don't forget, we need to find L. So anytime you are doing this, when you get the answer, some constant is equal to the final answer, you need to pick the exponential function on both sides so that it can help you to get your L. So here, e to the power 12 is equal to the L, right? So this is equal to e to the power 12. When you solve it, that's what you are going to get. Let's take more example. Let's practice. It's kind of very nice. Let's look at this, if we can use the L'Hopital's rule to do it. So plug in infinity. So this one is infinity, then x divided by infinity, then 3 divided by a big number is going to give us 0. So we get infinity to the power 0, which is one of them here. Yeah, infinity to the power. Okay, I didn't add infinity to power 0. So infinity to power 0 is here. So this is going to give us something like this. So we can apply. So the same process, right? But different functions. So let's assume that the limit as x approaching infinity of x to the power 3 on x is equal to L. So you see that we are going through the same procedure again. Limit x is approaching infinity. Pick ln on both sides. Divided by x is equal to ln of x, right? Then let's go. Limit x approaching infinity. This is going to give us 3 on x. Natural of x is equal to ln L. Then when I simplify this, I'm getting x approaching infinity. This is the same as 3x divided by that is equal to this. So this is kind of in the form of a function divided by g. So I can apply the L'Hopital's rule here. So let's do that. L'Hopital's rule, limit x approaching infinity, differentiate. You get 1 over x divided by 1, because when I differentiate ln x, that's what I'm going to get. And I'm going to have something like this, and make a log of L like this. Let me continue from here. Simplify. We get limit as x approaching infinity. We are going to have 3 divided by x is equal to the natural log of L. And then plug in infinity. We are going to get 3 divided by infinity. This 3 divided by infinity is 0, and this is this. Pick e on both sides, and your L or this one is going to be 1 is equal to L. So this limit is also equal to 1. So it's kind of very simple. I'll give you a trial question to do. Oh, I love this question. Yes, I love this question. This is a property that I learned. I think it said I should learn the formula, but when you use the L'Hopital rule, it actually tells you, oh, okay, this is what we are looking for. So first, let me plug in infinity. 1 plus a divided by infinity all to the power infinity. So this is 1 plus 0 to the power infinity, and this is 1 to the power infinity. So let's solve and learn this property. Now, what are we going to get from here? Now, this is kind of something like this. This kind of something like the same process, right? Limit x is approaching infinity, 1 plus a over x is equal to L. Pick natural log on both sides. So limit x is approaching infinity, natural log of 1 plus a over x, and this is natural log of L. And then from here, I have limit x approaching 0, x approaching infinity, x down, limit 1 plus a over x is equal to ln x. So since we need function divided by function, I'll write x as um, 1 divided by x, right? And this is going to give me this. So from here, I'm going to have limit x approaching infinity. And when I simplify this so that I can differentiate it, so this is x to the power minus 1. Now we can apply the L'Hopital's rule. So let's differentiate. I'm going to have limit x is approaching infinity. When you differentiate a ln function, we said 1 divided by what is inside the bracket. So 1 plus a divided by x times you differentiate what is inside the bracket. When I differentiate 1, I'll get 0. When I differentiate a over x, now a over x is the same as a x to the power minus 1. So differentiating this will give us minus a x to the power minus 2, right? So this is going to give us minus a x to the power minus 2 divided by, when I differentiate this, I'm going to have minus x minus 2. And then this is equal to the natural log of L. Now let me divide this guy. Let me shift it to the other side small so that I can use the space there to write. Good. So let's divide this one into 2. Now from here, let's do the simplification from here. So I'm going to have limit x is approaching infinity. I'm having 1 divided by 1 plus a over x. And then this is times minus a divided by x squared divided by, well, let me do the divided by like this. Divided by, so divided by this is the same as minus 1 over x squared, and this is equal to the natural log of L, right? Ln L. Pardon me if you are not seeing from there. That one is ln L. So let's try and simplify, because right now we need to simplify before we can think of plugging in the infinity. So when I simplify this, I'm going to have 1 divided by x plus a divided by x, right? So this is divided by 1. So x times 1 is here. Then 1 times a is here. Then 1 times x is here. Then this is like times minus a divided by x squared. Then this will be times minus x squared, right? And then I'm going to have this one to be equal to natural log of L. Limit x approaching infinity. This is the same as x divided by x plus a. Because of this one is over 1, so it will reciprocate it, times minus a divided by x squared times minus x squared is equal to the natural log of L. We are almost there. One of the x here will cancel one of the x here, or even the x squared here will cancel the x squared, because this one is multiplication, right? So x squared will cancel the x squared. So I'm going to have limit x approaching infinity. I'll multiply this one by this. So I'm going to have minus ax divided by x plus a. Then remember, I said This will cancel this. Okay, the minus and minus will be positive, so there will not be minus here. And this one should be equal to L. Can I plug in infinity? Let's plug in infinity and see. When I plug in infinity here, this one will be infinity and this one too will be infinity again. So what we need to do is we need to differentiate again. So let's do another differentiation. L'Hopital's rule. So when I differentiate the top, I'm going to get A. And when I differentiate the down, I'm going to get 1, right? Which is equal to the natural log of L. And then, limit as x approaching infinity of A is equal to this. Now we know that limit of a constant, A is a constant, is the constant. So this is going to give us A is equal to the natural log of L. And then as we said, we need to pick E on both sides. So E to the power A is equal to E to the power ln L. And this is going to give us L to be equal to E to the power A. So this is the property that I was talking about. So you see that this function here is going to give us, this is the same as E to the power A. So you see that if we are, this is a property that is very popular whenever you are doing limits. So this is equal to E to the power A. So E to the power the A here. So you see that if I change the limit and I put, let's say 2A, this one will be equal to E to the power 2A. So you look at what is in here and then you pick E to pick that. But the modification should be working here, right? It should also be working from there. So basically that's what you are going to get from this. Right. So this is kind of very simple. Just take time and then be working through. So this is your trial example, right? So try this and leave your answer in the comment section. As I said, I appreciate you for taking some time learning with me and then solving this and leaving your answer in the comment section for me to also reply to this. So try this. So I just did this L'Hopital rule. I should have done it in the limit side. So we are going to continue our differentiation and we are going to talk about implicit differentiation in the next video. So see you in the next video.